Welcome to this coding walkthrough. Today, we're tackling LeetCode problem number 1753, maximum score from removing stones. This problem challenges us to maximize the score by strategically removing stones from three piles. Let's dive in to explore the approach, break it down step by step, and solve it together. In this problem, we are tasked with maximizing the score from removing stones from three piles. These piles are represented by three integers, a, b, and c, which indicate the number of stones in each pile. On each turn, you can choose any two piles that still have stones remaining and remove one stone from each of the chosen piles. This action contributes 1 point to your score. The game continues until there are fewer than two piles with stones left, and at that point, the game ends. Your goal is to return the maximum score you can achieve by strategically choosing which piles to remove stones from. The input consists of three integers, a, b, and c, while the output is a single integer representing the maximum score you can obtain. Let's explore some examples to better understand the problem. Consider the first example where a equals 2, b equals 4, and c equals 6. The output in this case is 6. Here's how we can achieve that score. First, we choose two stones from piles b and c, leaving the piles at 2, 3, and 5. Next, we repeat the same operation, removing stones from piles b and c again, leaving 2, 1, and 4. Then, we switch to removing stones from piles a and c, leaving 1, 1, and 3. We repeat this step, reducing the piles to 0, 1, and 2. Finally, we take two stones from piles b and c, resulting in 0, 0, and 1. At this point, no more moves are possible since fewer than two piles have stones. The total score is 6, as each turn contributed 1 point to the score. Now let's look at another example where a equals 4, b equals 4, and c equals 6. In this case, the maximum score is 7. Here's the sequence of moves. Start by removing stones from piles a and c, leaving 3, 4, and 5. Then, choose stones from piles b and c, resulting in 3, 3, and 4. Next, take stones from piles a and c, leaving 2, 3, and 3. Follow this by choosing stones from b and c, leaving 2, 2, and 2. Then, remove stones from piles a and b, leaving 1, 1, and 2. After that, take stones from piles a and c, leaving 0, 1, and 1. Finally, remove stones from piles b and c, leaving all piles empty, 0, 0, 0. The game ends with a maximum score of 7. This example demonstrates how careful choices can maximize the number of turns and, consequently, the score. Next, let's examine an example where a equals 1, b equals 8, and c equals 8. The maximum score in this case is 8. Here's how to achieve it. Start by repeatedly removing stones from piles b and c until they are reduced to 1 stone each, leaving the piles at 1, 1, and 1. At this point, take stones from piles a and b, leaving 0, 0, and 1. The game ends here as no more moves are possible. The total score is 8. Notice that when one pile is significantly smaller than the other two, the strategy typically involves exhausting the two larger piles first, as long as the smaller pile still has stones to participate in moves. To summarize, if two piles become empty, no further moves can be made, and the game ends. Additionally, if one pile contains significantly more stones than the other two combined, the maximum score is limited by the sum of the smaller two piles stones, since each move requires two piles. On the other hand, if all three piles have an equal number of stones, the maximum score is achieved by repeatedly choosing any two piles. An important observation is that the maximum score is always bounded by half the total number of stones, as each move removes two stones. To simplify the process of determining which piles to choose, sorting the piles in descending order at each step ensures that you always pick the two largest piles available. This strategy helps maximize the score in an efficient manner. To solve LeetCode problem number 1753, maximum score from removing stones, our goal is to maximize the number of moves by repeatedly removing one stone from two of the three piles until at least one pile is empty. The problem allows us to explore different strategies, starting with the brute force approach. Here, the intuition is straightforward. In each step, we subtract one stone from the two largest piles until one of them runs out. This can be implemented with a basic loop that compares the sizes of the three piles and makes the necessary updates. However, while simple to understand and implement, this method isn't efficient for larger inputs. Its time complexity is proportional to the maximum size of the piles because we process each pile individually until it becomes empty. This inefficiency arises because it doesn't take advantage of deeper observations about the problem, leading to unnecessary computation. Therefore, we must look for better alternatives. Another approach to optimize the process involves sorting the pile sizes at each step. By sorting, we can quickly identify the two largest piles to subtract stones from. This can be implemented by storing the three pile sizes in a list, sorting the list, and decrementing the largest two values in each iteration. Sorting ensures that we always know the correct piles to target, but it also adds computational overhead. Specifically, sorting during every iteration results in a time complexity of n log n for n iterations, which is an improvement over the brute force approach but still not optimal. Additionally, sorting repeatedly is unnecessary when we consider the mathematical relationships governing the problem. The most efficient method emerges when we use a mathematical approach. Here, the key insight is that the maximum number of moves is constrained by the total number of stones divided by 2, or the sum of the two smallest piles. This is because each move removes 2 stones, and the total number of moves is naturally limited by the total stone count. Furthermore, if the largest pile is greater than the sum of the other two, the number of moves is restricted to the sum of the smaller piles. By leveraging these observations, we avoid iterative processes altogether. The result can be computed directly using a formula, the minimum of the total stones divided by 2 and the sums of different pile combinations. This approach is incredibly efficient, with a time complexity of 1, as it only requires a few comparisons and arithmetic operations to determine the result. Ultimately, the mathematical approach is the best choice for solving this problem because it is the most efficient and avoids unnecessary computations like iteration or sorting. The breakthrough insight lies in understanding that the total number of moves is constrained by the sum of all stones and the relationship between the largest pile and the other two. This eliminates the need for step-by-step simulations, making the solution clean, elegant, and highly scalable. Given the problem constraints, where the pile sizes can go up to 10,000, this efficiency becomes crucial. While the brute force and sorting methods help in building intuition, they fall short in performance and simplicity compared to the mathematical solution. This approach not only minimizes computational complexity but also highlights how problem-specific insights can drastically simplify a solution. Recognizing these kinds of patterns is invaluable in competitive programming and real-world problem-solving, where efficiency and elegance are both critical. By focusing on the relationship between the total stones and the pile's balance, we transform a seemingly complex task into one that can be resolved in constant time. To solve the problem of maximizing the score from removing stones, we need to carefully manage the 3 piles of stones represented by the inputs A, B, and C. The first step is to sort these piles in descending order so that the largest pile is always first. This simple sorting ensures that we focus on the 2 piles with the most stones, which is critical for maximizing the number of moves. Next, consider the total number of stones across all piles. This gives us an upper bound for the maximum number of moves, since every move removes exactly 2 stones. However, there's an additional observation: if the largest pile has more stones than the combined total of the other two, the score is limited to the sum of the smaller piles, as they will deplete before the largest pile. These initial insights set the stage for an efficient and structured approach to the problem. The main logic of the algorithm revolves around repeatedly removing 1 stone from the 2 largest piles. As long as all 3 piles have stones remaining, you decrement the sizes of the 2 largest piles and then resort them to maintain the order. This ensures that the next move always targets the piles with the most stones. The process stops as soon as 1 pile becomes empty, since no further moves can be made. For edge cases, if any pile starts with 0 stones, no moves are possible, and the score is 0. Additionally, when all piles have the same number of stones, the algorithm depletes all piles evenly, maximizing the score. For optimization, instead of simulating each move, we can use a formula to directly compute the maximum score as the smaller of 2 values, half the total number of stones, or the sum of the 2 smaller piles. This eliminates the need for iterative operations and leverages mathematical reasoning for efficiency. The insights behind this approach highlight the importance of sorting. By keeping the piles ordered, the algorithm can always make optimal decisions at each step. The formula min, a plus b plus c, // 2, a plus b, elegantly combines the total number of stones with the pile distribution to calculate the maximum score without unnecessary computational overhead. This problem is an excellent example of greedy optimization, where making the best local choice, removing from the two largest piles, leads to a globally optimal result. For data structures, we use a simple array or list to store the three pile sizes, which allows for easy sorting. Sorting after each operation ensures the piles remain in descending order, making the decision-making process straightforward. Alternatively, the mathematical approach bypasses sorting entirely, reducing both complexity and runtime. To analyze the complexity of the algorithm, consider the operations involved. Sorting the three piles takes constant time, O(1), because there are only three elements. If we simulate each move, the time complexity becomes proportional to the total number of stones, total_moves. However, the mathematical approach eliminates the need for simulation, reducing the time complexity to O(1). For space complexity, the algorithm operates directly on the input values without requiring additional data structures, resulting in O(1) space usage. This makes the solution not only efficient but also lightweight, capable of handling the problem constraints seamlessly. The solution to LeetCode problem number 1753, maximum score from removing stones, involves repeatedly removing stones from the two largest piles until at least one pile is empty. The implementation begins by receiving three integers a, b, and c, representing the number of stones in the three piles. First, the input piles are sorted to ensure that the two largest piles are always processed first. Sorting simplifies the logic because we can remove stones from the two largest piles directly and then resort the piles after each operation. Next, we initialize a variable score to 0, which will keep track of the number of moves, or stones removed. The main part of the algorithm is a while loop that continues as long as the second largest pile is not empty. This condition ensures that we can still remove stones from the two largest piles. Inside the loop, we decrement the counts of the two largest piles, piles 2 and piles 1, and increment the score by 1. After each operation, the piles are resorted to maintain the invariant that the two largest piles are always at the end of the list. The loop terminates when the second largest pile becomes empty, at which point no further moves can be made. The final value of score is returned as the maximum number of moves possible. This implementation is efficient because the sorting operation, which is the most expensive step, is performed on a fixed size list of three elements. Thus, it runs in constant time. The overall complexity of the algorithm is O(n), where n is the number of moves made, as each move involves fixed time operations like sorting and decrementing. Edge cases are handled naturally by the algorithm. For example, if one or two piles are initially empty, the loop never runs, and the return score is 0. Similarly, if all piles have the same number of stones, the algorithm correctly balances the removals until two piles are depleted. In summary, this solution is both concise and efficient, leveraging sorting and careful management of the piles to maximize the score in the stone removal game. Here, we start by importing the necessary utility class, arrays, to help us in sorting operations. The method maximum score begins by taking three integers, a, b, and c, representing the sizes of the three piles of stones. We store these values in an array called piles, which makes it easier to manage and sort them. Next, we initialize a variable score to 0, which will keep track of the total number of moves we make while removing stones. The core logic of the method is implemented inside a while loop. The loop runs indefinitely, but we will include a condition to break out of it when one specific scenario occurs. Inside the loop, we sort the array piles to ensure the two largest piles are always positioned at the end of the array. This step guarantees that we can repeatedly work with the largest two piles in each iteration. After sorting, we check if the second largest pile, which is now located at piles 1, has become empty. If it has, this means no more moves can be made, so we break out of the loop. If the second largest pile is not empty, we proceed to remove one stone from both of the two largest piles. This is done by decrementing the values of piles 2 and piles 1. After removing the stones, we increment the score variable by 1 to reflect the move we just made. This process continues until the loop is terminated, which happens when the second largest pile becomes empty. Finally, once the loop ends, we return the score, which contains the maximum number of moves we were able to make while removing stones. This solution effectively leverages sorting and greedy strategies to ensure we maximize the score in every iteration. To solve the problem, we start with an example where the input piles are A equals 2, B equals 4, and C equals 6. First, we initialize by sorting the piles in non-decreasing order, so we get piles equals 2, 4, 6. At this point, the score is 0 since no stones have been removed yet. Next, we begin the process of removing stones. In the first iteration, we take one stone from the two largest piles, which are 4 and 6. This reduces them to 3 and 5, making the updated piles 2, 3, 5. We then sort the piles again to maintain the order, though in this case, the order remains the same. The score increases by 1, reflecting the stones removed. In the second iteration, we repeat the process. Taking one stone from the two largest piles, 3 and 5, reduces them to 2 and 4. The updated piles are 2, 2, 4, and after sorting, the order remains 2, 2, 4. The score now increases to 2. Now, we continue by removing stones in subsequent iterations. In the third iteration, we take one stone from the two largest piles, 2 and 4, reducing them to 1 and 3. The piles are now 2, 1, 3, and after sorting, they become 1, 2, 3. The score increases to 3. In the fourth iteration, we take one stone from the two largest piles, 2 and 3, reducing them to 1 and 2. The piles become 1, 1, 2, and sorting keeps them in the same order. The score is now 4. In the fifth iteration, we remove one stone from the two largest piles, 1 and 2, reducing them to 0 and 1. The piles are updated to 1, 0, 1, and sorting gives 0, 1, 1. The score increases to 5. In the sixth and final iteration, we take the last possible stone from the two largest piles, 1 and 1. This reduces both to 0, resulting in piles equals 0, 0, 0. At this point, no more moves are possible since all the piles are empty. The final score for this example is 6. Moving to a second example with input piles A equals 1, B equals 8, and C equals 8, we first sort the piles to get 1, 8, 8. The score starts at 0. In the first iteration, we remove one stone from the two largest piles, 8 and 8, reducing them to 7 and 7. The piles become 1, 7, 7, and after sorting, the order remains the same. The score increases to 1. With the piles now at 1, 7, 7, we continue removing stones in a series of iterations. In the second iteration, we take one stone from 7 and 7, reducing them to 6 and 6, making the piles 1, 6, 6. Sorting keeps the order the same, and the score becomes 2. Similarly, in the third iteration, we remove a stone from 6 and 6, reducing them to 5 and 5, giving piles 1, 5, 5, and a score of 3. This process continues as we repeatedly remove stones from the two largest piles. The piles progress through 1, 4, 4, 1, 3, 3, 1, 2, 2, and finally 1, 1, 1, with the score increasing to 7. In the last step, we remove one stone from 1 and 1, leaving piles 0, 0, 1, and a score of 8. At this point, no further moves are possible, and the final score for this example is 8. Finally, let's look at a third example where the input piles are A equals 3, B equals 3, and C equals 3. We start by sorting the piles to get 3, 3, 3, with the score initially set to 0. In the first iteration, we remove one stone from the two largest piles, reducing them to 2 and 2. The piles become 2, 2, 3. After sorting, the order remains the same, and the score increases to 1. Next, we take one stone from the two largest piles again, 2 and 3, reducing them to 1 and 2. The piles are updated to 1, 1, 2, and sorting keeps the order as is. The score becomes 2. In the last iteration, we remove one stone from the two largest piles, 1 and 2, reducing them to 0 and 1. This leaves the piles as 0, 0, 1, and the score increases to 3. With no further moves possible, the final score for this example is 3. To analyze the time complexity of our solution, we start by looking at the operations involved. First, the piles A, B, C are sorted. Since there are only 3 elements, this sorting operation is constant time, or O1. Next, the while loop continues as long as the second largest pile has stones remaining. Within each iteration, we remove one stone from the 2 largest piles. This removal is a simple O1 operation. After removing the stones, the piles are resorted, which is again an O1 operation because the size of the array remains fixed at 3. The loop runs at most s/2 times, where s is the total number of stones across all piles, because 2 stones are removed in each iteration. Combining all these steps, the dominant factor in the time complexity is the while loop, which runs O(s) times. Thus, the total time complexity of the solution is O(s), or s equals a plus b plus c. Now, let's consider the space complexity. The input consists of 3 integers, a, b, and c, which are stored in constant space. Additionally, we create a list called piles to hold the 3 pile sizes. Since the size of this list is fixed at 3, it also requires O1 space. Other variables, such as score, are simple integers and do not require additional memory beyond constant space. There are no recursive calls or dynamically allocated data structures in this solution, so no extra memory is used. Overall, the space complexity of the solution is O1, as the only memory overhead comes from a few fixed-size variables. Let's compare the optimized approach with a brute force alternative. A naive brute force method would involve exploring all possible combinations of removing stones from the 3 piles and calculating the maximum score. This approach would lead to an exponential time complexity of O2 to the power of s, where s is the total number of stones, because of the sheer number of combinations to evaluate. Additionally, it would likely require extra memory to store intermediate results, resulting in a higher space complexity. In contrast, the optimized solution avoids this inefficiency by always removing stones from the 2 largest piles, ensuring we maximize the score in each step without needing to explore all combinations. By resorting the piles in each iteration, the solution maintains correctness while achieving a time complexity of O(s) and a space complexity of O1. This makes it far more efficient than the brute force approach. Finally, let's break down the best, average, and worst case scenarios. In the best case, the piles are already balanced such that the smallest pile becomes empty after just one iteration. Here, the time complexity is simply O1. In the average case, the piles are distributed randomly, and the loop runs approximately s/2 iterations, giving us a time complexity of O(s). The worst case occurs when the piles are perfectly balanced, meaning the loop runs the maximum possible number of iterations, which is also s/2. Even in this scenario, the time complexity remains O(s). To confirm this mathematically, each iteration involves removing 2 stones and sorting the 3 piles, both of which are constant time operations. Since the number of iterations is proportional to the total number of stones, the overall time complexity is O(s). The space complexity remains O1 throughout, as no additional memory is used beyond the fixed-size variables and array. When solving this problem, there are several common mistakes to avoid. First, not sorting the piles or identifying the 2 largest ones before each operation can lead to suboptimal moves. This is critical because the goal is to always remove stones from the piles with the most stones, maximizing the score. Next, many people overcomplicate their solution by trying to use advanced data structures like heaps, which aren't necessary here. Since there are only 3 piles, simple sorting or comparisons are sufficient to solve the problem efficiently. Another frequent oversight is ignoring edge cases, like when one pile has significantly fewer stones than the other 2. For example, if one pile has just 1 stone and the others have 1,000, it's crucial to adjust your strategy to handle this imbalance correctly. Additionally, while recursion might seem like a natural approach, using it without memoization can lead to exponential time complexity and poor performance. Finally, it's important to understand the termination condition. The process should stop as soon as one pile becomes empty. Mismanaging this condition can result in unnecessary calculations or even infinite loops, which should be avoided. To perform well in interviews, it's essential to focus on the key insights of this problem. At its core, the problem is about greedily selecting the 2 largest piles at every step, ensuring that you deplete the largest piles first to maximize the number of moves. This highlights your ability to simplify and solve problems efficiently. Additionally, recognizing the underlying pattern is crucial. This is a classic example of a greedy algorithm, and discussing how it relates to resource allocation problems can demonstrate your problem-solving depth. Another key point to emphasize is the optimization strategy. By explaining how sorting or direct comparisons reduce the complexity to just log 3 per operation, you can showcase your understanding of efficiency. Be prepared to discuss edge cases as well. For instance, if the piles are already empty or one pile is significantly smaller than the others, you should show that you can handle these scenarios gracefully. These discussions can make a strong impression on your interviewer. This problem also connects to several related problems that can help deepen your understanding of greedy algorithms. For example, LeetCode 1405, longest happy string, involves maximizing results under specific constraints, similar to how you manage the piles in this problem. Another related challenge is LeetCode 1648, sell diminishing valued colored balls, which focuses on maximizing profit by selecting resources in descending order, again, a greedy strategy. LeetCode 1833, maximum ice cream bars, is another example where you aim to maximize the number of items purchased, emphasizing the importance of prioritization. Finally, LeetCode 1353, maximum number of events that can be attended, demonstrates optimizing resource allocation over time. These problems share common themes, and solving them can strengthen your ability to recognize and apply greedy strategies across different contexts. There are also alternative approaches to solving this problem, each with its own trade-offs. The optimal method is a greedy approach using sorting or direct comparisons to identify the two largest piles at each step. This approach is efficient, with a time complexity of log 3, where n is the number of moves. While sorting or comparing may seem repetitive, it's computationally minimal given that there are only 3 piles. Another option is to use a priority queue, or max heap, to always retrieve the largest piles. This works well for scenarios with more piles but adds implementation complexity compared to simpler methods. Recursive backtracking with memoization is another alternative, where you explore all possible moves while caching results to avoid redundancy. While this demonstrates a strong understanding of recursion and dynamic programming, it's less efficient and has higher space complexity. Finally, a mathematical insight reveals that the maximum score is bounded by the sum of the two smallest piles. Using this insight, you can derive a formulaic solution to avoid iterative simulations, though it may require a deeper understanding and careful derivation, which can be challenging in an interview setting. Great job! We reviewed the problem, broke down the optimal solution, and discussed key takeaways for similar challenges. Remember, practice is key to mastering these concepts. Thanks for watching, and I'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!